In this video, we're going to have a look at two examples of geometric proofs using the scalar product. Some facts that we can use to help us prove some of these facts about shapes are, for example, when we have two non-zero vectors A and B, if the scalar product equals 0, then we know that these two vectors are perpendicular. And conversely, if we know that they're perpendicular, then the scalar product will equal 0. Some other properties of the scalar product that we need to remember are shown below. And it's to do that when we scalar product two vectors, it doesn't matter the order that we scalar product them in, we'll always end up with the same value. When we've got a vector scalar product with a multiple of another vector, that it doesn't matter where that multiple is, we've called that multiple lambda. And one of the important ones that we've been using a lot recently is when we are scalar producting the same vector by itself, we know that the result is the magnitude of that vector squared. So using the facts that we know about the scalar product and its properties, let's have a look at our first example. We want to prove that the diagonals of a rhombus are perpendicular to each other. So what we're wanting to prove is when we draw in the diagonals, they cross or intersect at 90 degrees. So we've got this rhombus here, rhombus OABC. We're going to call OA vector A and O to C vector C. So to start our proof, we're first going to define the two diagonals that are involved in the rhombus, the diagonal OB and the diagonal AC. So we can say OB is equivalent to moving from point O to point B in that direction. So we're going to do vector A plus vector C. Or we could do vector C plus vector A. We know if we go from OA to AB, AB is equivalent to OC because we know in a rhombus opposite sides are equal. We also know that AC, the other diagonal, moving from A down to C, we're going to have to move back to O, so that's going to be negative vector A plus vector C. So now that we've defined those two diagonals as vectors, let's see if we can prove that the diagonals are perpendicular to each other. Now, thinking about the scalar product, we know that when two diagonals are perpendicular to each other, the dot product equals 0. So we want to prove that this is the case. So we're going to perform the scalar product between the two diagonals. Okay, so OB, scalar product with AC, where we've got A plus C, scalar product with negative A plus C. So we've got negative A times A plus A times C, take A and times C, and C times C. So going through with our properties that we know exist, we've got our first one here. We've got, this will be worth negative A squared as a scalar. We've got plus A dot product with C, take A dot product with C, so we know that they're going to cancel. And then we've got vector C dot product with vector C, which we know is going to come out with a scalar of C squared. Remember, when we're writing the scalar, obviously it doesn't have the line underneath, the A is the same as saying the magnitude of vector A. So we could actually rewrite this as the negative magnitude of A squared plus the magnitude of C squared. What we have to realise, because we're dealing with a rhombus, the size of vector A is equivalent to the size of vector C, because we know for a fact that all sides of a rhombus are equal in length. So, because we know that the magnitudes of each of these vectors are equivalent, we can rewrite our solution here to say negative a squared plus c squared is equivalent to saying negative c squared plus c squared, or is equivalent to negative a squared plus a squared. And both of these equal 0. Therefore, we have proven that OB is equivalent to AC. And then we can say, hence, the diagonals of a rhombus are perpendicular to each other. In our second example, we're going to prove Pythagoras' theorem, and this is one that we're indeed very aware of. So we've got a right triangle here to the right. We've called it triangle O or AOB, and the O is where the 90-degree angle or right angle is. We've defined OA as vector A and O to B as vector B. So what we essentially want to do, because we know that A squared plus B squared equals what we would call C squared in when we would normally use Pythagoras' theorem, we're using vectors to represent it. We basically want to say that, OA squared plus OB squared should equal AB squared. So that's essentially what we want to prove is actually true. So let's first define AB in terms of vectors A and vectors B, because that's the result we want to prove here. So to travel from A to B in this direction, we're going to have to go negative A plus B. Okay, so what we're going to do now is use that, as well as the fact that a vector multiplied by itself, a vector dot product with itself is equal to its magnitude squared. So we're going to use that fact. I could write this in another way, saying, a vector times a vector is just its magnitude squared. Okay, to prove that AB squared is equal to OA squared plus OB squared. So let's start with that. We want to prove that AB squared is equal to OA squared plus OB squared. Okay, so let's start with this left side. This is going to be worth AB dot product with AB. And on the right side, this would be OA dot product with OA plus OB dot product with OB. Let's put it in terms of vector A and vector B now. So we've got negative A plus B dot product with negative A plus B. And this should be equivalent to vector A dot product with vector A plus vector B dot product with vector B. Okay, so let's perform this dot product on the left. So we're going to have negative A dot product of negative A plus we're going to have, it's going to be a take, so let's do that straight away. So take vector A times vector B, take vector A dot vector B, plus B dotted with vector B. And on the right side, we've got the scalar result of vector A dot product with vector A and vector B dot product with vector B. Now, if we have a look at this section on the left, we can simplify negative vector A dot product negative vector A is A squared, and vector B dot product with vector B is just going to be the scalar B squared. So now we need to consider these two values or terms left. The one thing we do know, if we go back to the diagram about vector A and vector B, is they are at 90 degrees, because we know for a fact that we're dealing with a right triangle. So when we consider that fact, we're going to pull on the fact that vector A dot product with vector B is equal to 0 when A and B are perpendicular. So we know that this value here equals 0 and this value here equals 0. So we've got take 0, take 0. And on our right side, we've got A squared plus B squared. Okay. So when we neaten this up, we find that our right side and our left side are equivalent. Hence, we have proven Pythagoras' theorem. We can therefore say that AB squared is equivalent to OA squared plus OB squared. So hence, we have proven Pythagoras' theorem using vectors. So that's again going back to using those facts about and the properties of the scalar product. So now it's your turn. I'd like you to have a go at the following question about triangle OAB, which is an isosceles triangle. So see if you can construct a diagram of this triangle, giving you a hint that I would put vertex O at the top, and see if you can prove that OH is perpendicular to AB.